In this video, we're going to cover section 1.8, temperature dependence of rate constants. As mentioned previously, rate constants are generally temperature-dependent quantities. Experimentally, it is observed that for many reactions, a plot of the natural logarithm of the rate constant against the inverse of the temperature demonstrates a linear behavior. We refer to this as a Arrhenius behavior. The following empirical relationship between temperature and the rate constant is known as the Arrhenius expression. As you can see in this expression, we have the rate constant being equal to a product of the frequency factor, A, or the Arrhenius pre-exponential factor, all multiplied by this exponential term, e to the minus EA, which is our activation energy for the reaction, divided by R and T, where R is the molar gas constant and T is temperature in Kelvin. The units of the pre-exponential factor, these are always identical to those of the rate constant, and these will vary depending on the order of the reaction, as we've seen previously. The activation energy is in the units of energy per mole, and we will normally report that as a kilojoule per mole. If we take the natural logarithm of the Arrhenius expression, we end up with the following linearized form of that expression, where the ln of k is equal to ln of a minus EA over R multiplied by 1 over t. So again, if we plot the logarithm of the rate constant against the inverse of temperature, we will find that if there's a good correlation between temperature and the rate constant, which we see for Arrhenius behavior, the slope of that fit will be equal to minus EA over R. So it'll be a negative slope, and the slope value will be a quotient, the activation energy divided by the molar gas constant. And the y-intercept for that particular plot will be equal to the natural logarithm of the Arrhenius pre-exponential factor. So for the Arrhenius plot, once again, the natural logarithm of the rate constant against the inverse of the temperature in Kelvin. If the reaction follows Arrhenius behavior, a linear Arrhenius behavior, we'll see a slope that represents the activation energy divided by the molar gas constant, and a y-intercept that allows us to determine the pre-exponential factor. Now we can also assess Arrhenius behavior qualitatively by looking at the relative steepness or shallowness of a slope. So if we have a fairly steep slope, that is a high activation energy, this signifies that the rate constant for that reaction is strongly dependent upon temperature. So a small change in temperature has a dramatic effect on the rate constant of the reaction. If we have a scenario in which the activation energy is pretty much equal to 0, this would imply or explicitly tell us that the rate is independent of temperature. And we see this with certain radical reactions, that they're temperature independent due to their high reactivity. And finally, we could have a third scenario where we have a fairly small activation energy. So a low activation energy, this signifies that the rate constant varies only slightly with temperature. So we often see this with gas phase reactions where changing the temperature of the system by 10 or 20 Kelvin doesn't cause a dramatic increase in the reaction rate. Whereas if that reaction was carried out in solution, we would expect to see a significant increase in the rate of the reaction as the temperature is increased to that extent. Now, the origin of the energy term in the Arrhenius expression can be understood as follows. The activation energy corresponds to the energy needed for the chemical reaction to occur. Now, we often envision a chemical reaction as occurring along some energy profile, as shown in this figure. If the reactants have an energy greater than the activation energy, the reaction can proceed. And the exponential dependence on the activation energy, this represents the fraction of molecules with sufficient kinetic energy to undergo a reaction. As the activation energy increases, the fraction of molecules with sufficient energy to react, they will decrease, as will the reaction rate. Now, once you know the activation energy of a reaction, you can take a rate constant at a particular temperature and you can predict how that rate constant will vary as the temperature is changed. And so a very useful and common expression is shown here, and I'll quickly go through the derivation of it. Here we see our Arrhenius expression, the linearized form of it, and we have it expressed as a rate constant K1 at a temperature T1. So that's the rate constant at a particular temperature. Now, if we write out the same expression, but now express the rate constant at a different temperature, that is K2 at T2, if we take these two expressions and we subtract them from one another, we end up with the following expression. So again, if we subtract the terms on the left-hand side, ln K2 minus ln K1, that is equal to minus EA over RT2 plus EA over RT1. And you'll note that we're assuming that the pre-exponentials are identical in this particular scenario, and so they will cancel out when we subtract these two equations from one another. With a little bit of rearrangement, primarily taking the activation energy and the Molar gas constant out in front, we're left with this particular expression, where the ratio of the rate constants, the natural logarithm of that ratio, is equal to EA over R, and then in brackets we have a difference between the two temperatures. And so if we use this expression, and if we know some information about the value of a rate constant at a particular temperature, we can predict, if we know what the activation energy is, what the value of the rate constant will be at some new temperature. Another way in which this expression can be used is that if we have two temperatures and two rate constants at those respective temperatures, we can calculate the activation energy. In many ways, this is similar to just taking the slope from two data points. So if you have any questions about the temperature dependence of rate constants, and specifically the Arrhenius expression and how it's used, by all means, send me an email. Thank you.